Welcome to video 7 in the course G07 on phylogenomics. Here we're going to talk about the molecular clock. So the molecular clock requires that your samples have a temporal dimension, preferably the exact date on which they were sampled. Your isolation is okay, but it's not great if you want very crude estimates. So we can compare the number of mutations per sample as accumulated since the root of the phylogeny, and compare that to the number of mutations to the time information based on that approximation for the root as well. So we're looking at the branch lengths from the root to each tip and compare that for time and look at the correlation between those two variables. So there's an example here on our right where we think about the most recent Ebola virus outbreak from 2013-2016 in Western Africa. And we can compare that to previous ones, such as that in the DRC, or Zaire, and older ones. And we can use the information and the timing of those samples and their genetic distance to estimate the correlation over time. So these can be collections of samples or individual samples. We just need a lot of them and sufficient time to have elapsed to really measure this accurately. So we can see here was when you fit a best fit line through this root to tip divergence. So you can see it's down here at 0 at the root. We can see that the root is somewhere around 1978-ish, maybe, with obviously this some variation in the exact estimates. And then we can see that when we're going up to the modern day, we're going up here. Well, obviously this image is from some years ago. You see that there is some noise in the different samples here, and this is not the most abundant collection, but it actually contains information for the different outbreaks. And what we should also consider is that the molecular clock may have varied over time as well. So it's not necessarily static. If you look at that 2013-2016 West African Ebola virus epidemic in detail, what we can kind of see is that the average rate of mutations per site was about 1.2 per kV per year. So it's 22.8 substitutions per genome per year is what it actually was estimated as. So that's looking at time on the x-axis and on the y-axis, the number of substitutions. As mentioned previously, then we can link time to the tree. So this is the time, this is the samples placed over time, represented in their phylogeny. So the actual genetic distance may not quite match this. This is an approximation. And what we can construct for each particular node, such as this one here, going back to the root, is a highest posterior density distribution, estimating when this occurred. So you can sort of see that this one here has a skewed distribution and has kind of a wide confidence interval. Same for this node here, corresponding to this branch here. Certainly the topology is correct, but the date, the timing is uncertain, and indeed the signal may vary across the tree. So there may be instances where we're able to get a more narrow, more certain estimate of the time interval when something occurred, or it may be tricky due to variation in molecular across our particular aligned region of interest. So if we look at that epidemic as well, there's lots of estimates of when particular bifurcations occurred. So you can see we've got near the epidemic source in Guadalquivir in Sierra Leone. We can see that's where it started. It's likely that there was a young toddler playing with some fruit or in her back garden, and it's hypothesized that, or seems reasonable certainly, that she somehow came in contact with a bat and somehow became unwell. Her parents became unwell. This was an acute illness. It spread on to people that with which they came into contact, and then also onto people within they came into contact after they passed away, and spread through the community. And you see this branch going from here, from Sierra Leone, from Guinea into Sierra Leone, Calahan. That's from there, and then this local one is here. And the question would be, from where did all these transmission chains emerge? And you can see that with this kind of a tree, that it's not necessarily quite clear the precise patterns that occurred because of the rapidity which with it spread between different peoples and transmitted much more quickly than it attained mutations. So you can kind of measure the signal here represented by the highest posterior density possible. You can see they vary themselves. One thing we learned from that study was that there was different estimates of the evolutionary rate or substitution rate. So you can see here, this is the substitutions per site per year. You can see that there's different estimates here that are very, very wide. One early one was from Gear et al. In 2014. I see the other ones here are a bit later. So what you see is that the later ones tend to conform to a lower rate, and you see their certainties are much higher. The Gear et al. Certainty was very low. So this was taken on early in the epidemic, where insufficient evolution time had elapsed, such that many of the mutations they were counting were likely to be deleterious, as well as neutral, and ones that were under positive selection. Whereas the other studies, longer time had elapsed, allowing that a more accurate estimate of the substitution rate to occur. So longer selection pressure had operated, eliminating the mutations that were more deleterious. So what happened here was that because the estimates are so wide here, if we got a result like this, it's so wide that it's really there's no information there. However, they did publish that. When we look at the combined public data estimate, down here we can see that their estimate was much higher, and that's a cautionary tale about kind of understanding uncertainty when you're estimating molecular clocks. Sometimes the signal is very strong, sometimes it isn't. And we have to acknowledge when it isn't, and it varies tremendously across different genomic regions and across different organisms. So this Ebola epidemic from 2013 to 2016 was the first one to use real-time genomic surveillance. It has common ancestry with the other lineages going back to 2004. It came slightly to spread from Central Africa to West Africa. It had a faster substitution rate compared to previous outbreaks rate. The Gear et al. Estimate was too high. We know that the true rate was actually 1.2 substitutions per KD per year. And we might see that as selection is effective over time, that this will fall slightly towards this rate here. If we look at SARS-CoV-2 in November 2022, the molecular clock rate was about 21.8. So you can see here over time going back to December 2019. And then we have our time on the x-axis and the mutations going from 0 up to about 30 on the y-axis. You can see that was our estimate. If we then roll on to going back to the origin to October 2021, the rate was now 24.0 substitutions per genome per year. So you note that included Delta. There's some erroneous sequences here above and below. What is evidence is that the molecular clock depended on the types of infections that occurred. So it might be skewed by chronic infections associated with the emergence of different variants, such as alpha, delta, and we can map on the older mutation rate there. So you see the molecular clock estimates for SARS-CoV-2 has increased over time. We go to October 2022, it's about 28.1. So Omicron has emerged. It's hypothesized that lineage was under strong selective pressure inside an individual or multiple individuals, and became rapidly much more fit and accumulated more mutations during that time. If we roll on then to more recently, October 2023, we're hitting about 30 substitutions per genome per year, depending on what exact samples that you take. This is just a sample of those that are sequenced. So you can see originally it was lower. This scale is not quite perfect. It was lower, but it's increased over time. So that was 21.8 at the start. It's increased to 30. So although it's hypothesized that the substitution rate estimates tend to decrease over time due to the more effective types of selection, for the SARS-CoV-2 pandemic, you can see that long-term chronic infections, which are absent in Ebola virus, may have had other impacts on our estimates of the evolutionary rate. So that's why what works for one organism may not work quite as well for other organisms, and we have to check our assumptions when applying these approaches. Finally, we can use these in terms of considering what clock rates are most pertinent if we're trying to model this effectively. So you'll hear about strict models where the mutation rate is fixed. We'll have relaxed ones where it varies, the mutation rate varies among lineages given certain parameters. And then there's also local mutation rates where it might locally vary within a particular clade. So the molecular clock has great power in terms of inference, especially for genomic epidemiology, but also needs careful consideration as to whether the signal is actually good or not. So please see the next video on virus adaptation where you think about this more clearly.